This video is sponsored by Brilliant.org. Head to Brilliant.org/MichaelPenn to try everything Brilliant has to offer free for a full 30 days. The first 200 of you will get 20% off Brilliant's annual premium subscription. Today we're going to look at something that I'll call the craziest definition of the derivative. So let's jump right into it. We're going to start with something called the forward difference operator, or sometimes the discrete derivative. I'll write that as delta applied to f of x is equal to f of x plus 1 minus f of x. And in fact, we have the following relationship between this discrete derivative and the regular derivative, and that is f prime of x is equal to the natural log of 1 plus delta applied to f of x. And so of course this is like a result, but I guess we could twist our minds to redefining the derivative like this if we really wanted to match our title up here. Okay, well, let's step back a little bit and maybe look at the question, what do we even mean by this natural log of 1 plus delta? Well, let's recall the following. Let's take the natural log of 1 plus t, where t is just like a variable, instead of like an operator like this. Well, notice that we can write this as the antiderivative of 1 over 1 plus t dt. And then we can expand that as a geometric series. So that's going to give us the antiderivative of the sum as n goes from 0 up to infinity of, let's see, it'll be minus 1 to the n times t to the n dt. That's because we have geometric series, the common ratio here is minus t. But now we can take the antiderivative term by term here, and that'll give us the following object. So we'll have the sum as n goes from 0 to infinity, and then we'll have minus 1 to the n, and then we'll have t to the n plus 1 over n plus 1. Okay, so that's the expansion here. But that gives us an idea of what we should talk about when we're talking about the natural log of 1 plus delta. And so perhaps this would be a way of thinking about this. So the natural log of 1 plus delta is equal to the sum as n goes from 0 up to infinity of, well, it's going to be minus 1 to the n over n plus 1, and then it'll be like delta to the n, where that means we're going to apply delta n times. I guess I should say n plus 1 times. You know, that was a little bit of a typo there. Okay, and generally when you see some sort of operator, like even a linear operator like a matrix, or like the derivative or so on and so forth, inside of a function, what that generally means is you interpret that as like the expansion, the power expansion of that function evaluated at this place. Okay, so let's maybe put a box around that. This is essentially what we're going to take as the definition of the natural log of 1 plus delta. Now, let's go ahead and look at some basic examples before we maybe look at this result more carefully. I'm glad you're here to learn math, but you get more out of active learning, and that's why I highly recommend you sharpen your skills with Brilliant. Brilliant's enormous library of learning content allows active learners like you to explore a variety of topics and skill levels, and Brilliant will support you every step of the way. You'll be able to master whole topics gradually in as little as 15 minutes per day, and learn anywhere, anytime, on your phone, tablet, or computer. Brilliant makes learning more like a game with features that let you challenge yourself and compete with others. I recently used their resources for inspiration in my Calculus 2 course, and I use it with my son who is in pre-algebra. See what I mean? Brilliant is an amazing tool that can help you improve. But we're scientists here, so don't take my word for it. You should test it for yourself by going to Brilliant.org/MichaelPenn. Treat yourself to the best hands-on learning experience. A 30-day free trial, and the first 200 people will get 20% off their annual subscription. Thanks once again to Brilliant for sponsoring today's video. So for our simple example, we'll look at f of x equals x cubed. And we'll start just by calculating delta applied to this, several times. Okay, so let's start with delta applied to x cubed. So that'll be x plus 1 cubed minus x cubed. But we can apply binomial expansion to the first term, and that'll give us an x cubed term, and then some other stuff. Well, the x cubed terms will cancel. And what we'll be left over with is 3x squared plus 3x plus 1. Now let's move on to delta squared applied to x cubed. So that's simply delta applied to the line that's right above. But delta is linear. I think that's pretty clear by its definition over here. So we can write that as 3 times delta applied to x squared. And then let's see, plus 3 times delta applied to x. And then finally, plus delta applied to 1. So by the definition over here, we can see that delta applied to 1 is 0, so we don't really need to worry about that. Then we can calculate the rest. So this will be 3, and then we'll have x plus 1 squared minus x squared, and this will be 3 times x plus 1 minus x. Okay, but then we can simplify this out and we'll see that it's 2x plus 1 and then plus 3, well, times 1. So putting this all together, we'll see that we get, let's see, 6x plus 6. Okay, great. And now let's apply this one more time. So delta cubed applied to x cubed. So that's going to be delta applied to the line that's right above. But delta applied to this is pretty clearly equal to 6. And then also we should point out that if we go higher, we will always get 0. That's because we hit a constant here. So in other words, delta m applied to x cubed is equal to 0 as long as m is bigger than or equal to 4. Okay, nice. But now let's do this calculation over here in light of what we've just seen. So natural log of 1 plus delta applied to x cubed. So the sum can stop at n equals 2, because n equals 2 is delta cubed. Everything else after that will be higher powers of delta. Okay, so we've got the sum as n goes from 0 up to 2. We have minus 1 to the n over n plus 1, delta to the n plus 1 applied to x cubed. But now we can use the calculations that we've just done above to simplify this fairly quickly. So the n equals 0 term will give us delta of x cubed. The n equals 1 term will be minus 1/2, and then delta squared of x cubed. And then finally the n equals 3 term will give us, and finally the n equals 2 terms will give us plus 1/3 delta cubed applied to x cubed. Now we can just insert what we had above. So this is 3x squared plus 3x plus 1 minus 1/2 times 6x plus 6, and then plus 1/3 times 6. But everything that we need to cancel does cancel. This 3x will cancel with this 6x because the 6x is attached to a half. And then this 1, this is minus 3, and that's plus 2. Those will all cancel as well, leaving us with 3x squared in the end. But of course, 3x squared is simply the derivative of x cubed. So we've just seen this magenta boxed equation actually happen with this simple example. Okay, so now let's see why this works in general, and then we'll look at some nice applications. Okay, so now we're going to give a hint about why this works in general. And before I do that, I'd like to give you a challenge, and that is to show directly, without using the strategy that I'm about to use, that if we apply natural log of 1 plus delta to x to the m, we in fact get m times x to the m minus 1. In other words, the power rule works here. And then that's like kind of enough in order to prove this result for nice functions. And what I mean by nice functions is those are functions that can be expanded as power series. But this is not the way we're going to do it. I actually worked out several pages of this calculation, and either I just didn't see a trick or it's like actually legitimately difficult. I don't know which one it is. But that being said, I never came up with a direct proof of this. And if I had, I think it's maybe too complicated to make a really nice video. Okay, so what we'll use is something that we proved in a previous video, and that is related to this thing that we called the formal Taylor theorem, which says that e to the d by dx applied to f of x is equal to f of x plus 1. Now you might say, well, what's e to the d by dx? Well, we'll use the same thing that we talked about over here, and that is whenever you have an operator wrapped up in a function, what I really mean is you expand that function as a power series, and then that's repeated applications of that operator. So in other words, e to the d by dx is defined to be the sum as n goes from 0 to infinity of, let's see, 1 over n factorial, and then the nth derivative with respect to x. Okay, so now let's see where we can go from there. Let's start with maybe delta applied to f of x, which is f of x plus 1 minus f of x by the definition right here. But now let's use this result to write f of x plus 1 as e to the d by dx applied to f of x. And then we'll rewrite f of x as maybe 1 applied to f of x. But now let's factor the f of x out of the right-hand side, leaving us with e to the d by dx minus 1 applied to f of x. Okay, but if that's how those operators act on an arbitrary function, that means that these guys are equal as operators. So in other words, delta is equal to e to the d by dx minus 1. So equating those two blue underlines and moving some things around, we'll see that e to the d by dx is equal to delta plus 1. Now we simply just have to take the logarithm, and we'll see that the derivative operator, d by dx, is the natural log of delta plus 1, thus achieving our result over here. Okay, so now what I'd like to do is give a couple of what I'll call applications. Really, they're just new proofs of existing results using this strategy. Okay, so our first application will be a new proof of a well-known sum identity. So I'm going to start from here. So let's take natural log of x. So let's take natural log of 2 times 2 to the x. So we're going to consider that function. But that's pretty clearly equal to the derivative of the function 2 to the x. Okay, but then in turn, since the derivative is equal to this natural log of 1 plus delta expansion, this is simply equal to the natural log of 1 plus delta applied to 2 to the x. But now we can expand the natural log of 1 plus delta like we had over here, and that'll be the sum as n goes from 0 up to infinity minus 1 to the n plus 1 over n plus 1, and then we'll have delta to the n plus 1 applied to 2 to the x. And now I'm going to take a little bit of a break from this and figure out what delta to the 2n plus 1 applied to 2 to the x is. And this is actually quite simple. So let's just apply delta to 2 to the x, and note that we get 2 to the x plus 1 minus 2 to the x. But we can pretty clearly factor a 2 to the x out of this, and we're left with 2 to the 1 minus 2 to the 0. In other words, 2 minus 1. So in other words, this is 2 to the x. So in other words, the discrete derivative applied to 2 to the x just gives us 2 to the x. This makes the number 2 sometimes called the discrete e, but that's kind of neither here nor there. But what that really means is that we can take this term right here and just replace it with 2 to the x. Because if you apply delta once and nothing changes, then if you apply delta as many times as you want, nothing also changes. But then this is a constant with respect to the sum. We can bring it out, and then we'll be left with the sum as n goes from 0 up to infinity of minus 1 to the n plus 1 over n plus 1. But now let's look at the extreme left and right-hand side and observe that we can just cancel this 2 to the x term, And we're left with a pretty classic sum identity. The sum is n goes from 0 to infinity minus 1 to the n plus 1 over n plus 1 equals natural log of 2. So again, we have this like kind of crazy way of getting at this sum identity. And honestly, until I put together this video, I had never seen this strategy for getting at this sum identity. I really like it. Okay, so let's look at one more. Okay, so our last application is going to require a bit of an exercise, which I won't work through. This is fairly straightforward. You can prove it with induction. And that is, if we take r discrete derivatives of x to the m, we get the following kind of crazy looking expansion. So it's the sum k equals 0 to r of minus 1 to the k plus m of r choose k, that's a binomial coefficient, and then x plus r to the m. And then furthermore, that's equal to 0 if r is bigger than m. Okay, so now we're going to use this exercise to come up with like the craziest expansion of a natural number. So let's take any natural number, m, and let's notice that m is the same thing as the limit as x goes to 1 of m times x to the m minus 1. I think that's pretty clear. But in turn, that's the same thing as the limit as x goes to 1 of the derivative of x to the m. Again, because the derivative of x to the m is simply m times x to the m minus 1. Oh, but the derivative can be written like this over here. So that's the same thing as the limit as x goes to 1 of the natural log of 1 plus delta applied to x to the m. But now we can expand that natural log of 1 plus delta using this series, and that'll leave us with the limit as x goes to 1, and then we'll have the sum as n goes from 0 up to infinity of, let's see, minus 1 to the n over n plus 1, and then delta to the n plus 1 applied to x to the m. But now we can apply this rule up here, this exercise, to this expansion. So that's going to give us the limit as x goes to 1. Then we'll have the sum, n goes from 0. We can actually stop at m minus 1 because of this rule right here. Everything higher would give us 0 when applied to x to the m. Okay, then we'll have minus 1 to the n over n plus 1. And then this, in turn, is the sum as k goes from 0 to, let's see, n plus 1 based off of this rule up here. And then we'll have n plus 1 choose k. And then let's see, we'll have x plus k plus 1 all raised to the m power. Okay, nice. And now what we'll do is simply apply this limit. So that'll take x and turn it into 1, and then we'll rearrange this a little bit. So this will be the sum as n goes from 0 up to m minus 1. And then inside of that will be the sum as k goes from 0 up to n plus 1. And then we'll have, let's see. Oh, I just realized I left out a power of minus 1 here. This should be minus 1 to the power n plus k plus 1. N plus k plus 1. So that'll combine with this minus 1 to the n to give us minus 1 to the k plus 1. Okay, so that was a quick fix. And then we'll have that is multiplied by 1 over n plus 1 from this term right here. And then in turn multiplied by the binomial coefficient n plus 1 choose k. And then finally multiplied by k plus 1 to the m power. And now let's just compare the left-hand side and the right-hand side and see this identity that we've just built. This crazy double sum, which is alternating, and it involves not only an expansion of k plus 1 to the m, but also some binomial coefficients, is just simply equal to the natural number m. So I haven't seen this identity anywhere. Maybe if you fool with it a little bit, it'll be a commonly known identity. But that being said, I like how it kind of easily falls out of this result over here. And if you stuck around this long, thank you. There should be the video on the screen about the formal Taylor theorem right now, which we used in this video if you'd like to check that out. And that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.